So for the, do you want to do the introduction?
I can. Yeah.
Yes.
Okay. So we're very happy to have Amnon Besser and Francois Escriva, who will be speaking on Frobenius lifts and point counting for smooth curves.
Thank you. So I'm going to be talking on a joint project with Work the Year. So where we're trying to make an algorithm that will hopefully be able to deal with arbitrary smooth curves. I think there's still some way to go before we can actually plug in an arbitrary curve and get out the number of points, but it certainly went a long way towards that. So again, the goal is to have this new method for point counting, and it's of the type that Kieran was talking about this morning, using Monsky-Washington cohomology. Timing is kind of a little bit difficult to say. So theoretically, it seems to be of the same, well, roughly the same complexity. Of course, Kieran's algorithm is only for hyperelliptic curves, but the sort of characteristic is that it's going to be linear in P in the characteristic of the field, and it's going to be cubic in the sort of size of the field, and then the dependence on the genus is somewhat unclear, but I think there's some sort of heuristic saying that it's going to be maybe G to the 7, so for plane curves. In general, it really depends a lot on the class of curves that you're working with. There's a preprint on the archive. I want to copy, so just search for, it's easiest to search for Francois. So there are sort of like, I would say, three new ideas going into the algorithm. The first one is that we want to, unlike the Teglai algorithm, where you do reduction in cohomology, so you have to take an arbitrary differential form and try to write it as a differential of something plus a combination of basis elements. We're going to use some methods for computing cup products. The second idea is sort of a new technique for making general lifts of Frobenius. And the third, which sort of combines, in some sense is relevant for both of these, is that you're going to be doing eventually some sort of a local lift of Frobenius. And I'll explain what local lifts means later. So first I want to explain what happens with what's the idea with cup products. So there's this thing that underlies a lot of what I do in some sense on curves, and that's the formula, starting from the formula of Serre for the cup product. So here you have a curve over a smooth complete curve over a fielding characteristic 0, should have said. Two forms of the second kind. For those of you who don't know what second kind means, it just means that it's a meromorphic differential and all of the residues are 0. So in particular, if you pick a point and you look at the expansion, even if the form has a singularity at that point, there's going to be the parameter is z, there's going to be negative powers of z, but the power z minus 1 doesn't show up. There's no term z minus 1 dz, and the consequence is that if you do formal integration, there's no logarithmic term. So all the terms in the expansion can be integrated. And then the formula of Serre says, which to be honest, I don't actually know of a reference from Serre himself for that, but everybody calls it Serre's formula. So the cup product is, so cup product here means you take two forms, so these two things give you classes in H1 of the curve, H1 the realm of the curve, and in cup product you get into H2, and then because it's a curve, there's a trace map to K, and the formula says that if you take this cup product, it's just given as follows, you go over all points, and the sum will be 0 for almost all points, you do the following, you take this form omega and you integrate it, and then you multiply by, so this gives you a function or power series expansion at x. You multiply by omega, again formally expanded at x, and then you just take the residue at x of this resulting formal one form. Now the thing to notice, the two things. One is, again, because this is of the second kind, there's no logarithmic term here. Second, of course, the integral is only unique up to a constant. If you look at the residue computation, you notice that this constant term is going to match with the residue term for eta, for the way that it affects this formula. And so it doesn't matter. You can just pick any point you want and integrate in whatever one where you want at that point. So that's Serre's formula. So the sum is of all points, and integral is a local integral just at that point, and the constant term is arbitrary. So what you can do with that, and is where I do something slightly more general or specific in the case of the p-adic. So let's say that my field now is a p-adic field, and you have what Coleman calls a wide open space. Let me spend a minute explaining what that is. So you pick your curve C, which is this big thing here, and then you start throwing away disks. Now the idea is usually you want to look at a curve here which has good reduction, and then these things, the bigger disks here, are these residue disks. So these are all the points that reduce to a given point. And then what you're doing, and that's essentially the idea of overconvergence, is that you're throwing away slightly less. So you should think of this as being a disk of radius 1, and you're actually throwing a disk of radius r, and that gives you ur. And I'm sort of treating u as kind of like the, I guess, the direct limit, maybe the inverse limit of the urs. But formally, I'm just picking in r sufficiently close to 1, and I'm working with that. So now what you can do if you have now just two forms, you just have a form on u, so it's a rigid analytic differential. So first of all, you can define a notion of the residue along this di, because the point is that you're letting yourself, I mean, the form exists on this sort of annulus that you had here in between these two disks, and on that it has an expansion into sort of an infinite Laurent series. And so there's a notion of a residue, which is just the term of dz over z. So again, it turns out to be well defined. And you can make kind of a tentative notion of second kind, meaning that on all of these disks the residue is 0. And you can have a cup product-like formula or pairing, which is just the same, exactly the same thing, except that you're just going to take the residue along the di. Now, the basic observation which you can make, which basically comes from a kind of a residue theorem, telling you that the residue on an annulus is the same as the sum of the residues on the points inside the interior of the annulus, is that if I have two forms of the second kind, and you throw away all the disks, including all the singular points, it's the same thing as taking the cup product using the Serre formula, or restricting to u, and then taking this pairing. Sort of cup product like pairing here. And what that means is that, see, the difference between u and c is that u is sort of too big. You usually don't have lifts of Frobenius on that. U is somewhat smaller, and you can have lifts of Frobenius over that, and that's exactly what Kieran does in this paper on hyperelliptic curves. So you pick so for that you take u, which is c minus all the Weierstrass disks, and you have a local lift of you have a lift of Frobenius, which is phi of xy, where x goes to x to the p, and y goes to some. Oh, and so the second coordinate is something in x and y. So back to this sort of thing. Now, on H1 of C, there's a Frobenius coming from the fact that the round cohomology is isomorphic to crystalline cohomology, and on crystalline cohomology, rigid cohomology, there's a Frobenius. And a basic fact is that this restriction from the round cohomology of C to the round cohomology of U is actually compatible with the Frobenius. So the fact that you can read off the cup product just in terms of U is really useful, because it tells you that on U you can do both the cup products and the Frobenius. So it's sufficient to doing essentially everything. And so the way that we're going to apply this is via this corollary. It tells you that if I have these two forms, and here I really should mean the cohomology, because phi of eta doesn't make sense, it's just means the class in the rank homology of omega, the class in the rank homology equals crystalline homology of eta. You take this cup product, it's the same as if you're restricting, I should have said restrict to U, you're restricting to U, you're applying phi just as by picking this lift of Frobenius and taking this pairing, this cup product pairing on U. So you have everything you need in terms of, and so now you can use linear algebra to compute the matrix of Frobenius. Now I'm sort of slightly cheating. Everything here has to be done in sort of a semi-linear way. The geometric language kind of doesn't lend itself so easily to this semi-linear thing. So it's better just stick with kind of like pretending that P is Q. It's a simple situation, but that's the Geist of things. So you have a basis for this Durand homology, and what you do is you first compute the cup product matrix. So you take all the combinations of forms you compute their cup product. Then you take this matrix that I can now compute, which is take all the forms and cup with the applying Frobenius to the other form. So that's the thing that I do using the previous corollary. And so then, well, I cannot swear on the direction of this. Somebody better control of directions can do, but it's sort of clear that the matrix of Frobenius is, if you have these two matrices, it's just given by taking m2, m1 minus 1 on either side, whatever, one of the sides. So that's the idea of applying cup products for computing the matrix of Frobenius. So that's the first idea. The second idea is sort of a general lifting of Frobenius. And let me sort of suggest that one of the problems with lifting Frobenius is that the lifting is not unique. If you think about, just take the case of plane curves, so what you have to do is you have to take, so you have, say, one equation fxy equal to 0, and you have to lift Frobenius, so that means that you have to write two coordinates, the new x and y, and they just have to satisfy one equation. So it's an underdetermined equation, which means you have a lot of freedom, and this freedom is problematic. Now, quite a long time ago, Ralph Berkman, in his thesis, wrote down sort of a general machinery for using this kind of Kedlaya-like algorithms for varieties, and he does write something about the lift of Frobenius, and you can see that it's sort of, so you do lift as you expect by Newton iterations, but because the system is underdetermined, in some sense you don't have a unique solution. At each step of the iteration, you just sort of apply a one directional inverse. So there's a lot of freedom here, and that turns out to be bad, and certainly for this local thing that I'll explain later, it's bad, and I'll show you that. But what's the idea of making a canonical lift of Frobenius? So again, I just explained the example of one equation with two variables, but that's really the general idea. So what you have one polynomial in two variables, coefficient say zp, and you assume that the reduction is non-singular, and what that means is if you take the partial derivatives, you'll be able to write so I mean it's going to be congruent to 1 mod the reduction of f. Some combination is going to be congruent to 1 mod the reduction of f. And then I'm going to lift rather arbitrarily these two new things that show up here, the p1, the p2, and the delta, two things in over zp. And then I write the general form of Frobenius. So Frobenius is going to be phi of xy is x to the p, y to the p, plus s times p1 x to the p, y to the p, p2 x p to the p, y to the p, and s is chosen to be congruent to 0 mod p, and solve a particular equation, which is this equation. All right? So the first thing to notice is if I have this equation, then basically by definition, right, f of phi, because here this is just phi, f of phi of xy is just going to be f of xy to the p times something. So in other words, if you started with two solutions to this equation, the phi of that is going to solve the same equation. So it is morphism of the curve defined by f. And this equation can be solved because if you look at what is its derivative with respect to s, so there's just one variable s, that's just this thing. And if you look at the way I set it up, of course, these things are just pth powers mod p. So this thing is basically just one modulo p. And so now you just apply Newton iterations, and there's a unique solution. So once P1, P2, and delta are chosen, and of the lift, sorry, P1, P2, of course, also mod P, there's some choice there. But once this choice is made, the lift is unique. Right. So now I'm going to explain the third idea, which is the local lifting of Frobenius. So you see, now I just do something locally at the disk P, and there's a parameter T for that. And what I need to do is I need to write down, in order to compute the residue, it's a completely local computation on this disk, for which I need an expansion of the Frobenius on this disk. And so, right, because once I have that, I just pull back one of the differential forms, multiply by the interval of the other form, and take the residue. So there's one naive global strategy for doing this. You just compute phi of x, y in terms of x and y. You compute x and y in terms of t, and then you apply that to phi, and then you compute the t of that locally at this thing. So that's the naive strategy. A much better strategy, and I think so we sort of understand theoretically why it's better, but it's also, I believe, better in computations, is you do the following thing. So write x, y as a consequently p1, p2, and delta in terms of this parameter t. Now you just look at the equation, and you solve this equation in terms of t. Yeah, there's no point, maybe not a power series, it's probably a sort of Laurent series, right? And then you again plug it into the formula for phi, and you get phi in terms of t. Now there's an advantage and a disadvantage to that. Disadvantage is because it's sort of a local strategy, you have to do this separately for each one of these removed disks. But the advantage is that rather than working with power series in several variables, the essential thing, the Newton iteration, is done just with power series or Laurent series in one variable. So the computation is much faster. So the two things we haven't done yet. One is, and that's is some question about how you actually lift from characteristic P to characteristic 0 in general. I mean, it's known that you can do this in general. So algorithmically, the situation is not so clear. And as I was discussing with Kion yesterday, he sort of suggested that it's probably enough to just do formally. So if you need precision P to the end, then you probably just need to somehow find a lift more to the end. It may or may not be true. It's not entirely clear. And the other thing is to find a basis for the cohomology. And I want to make two comments about it. One is that seems to be it's a problem of computing Riemann rock spaces, and there's some work on that. But in fact, it's probably not required. So one possibility is to just pick sort of a cyclic basis. So you just pick one differential form of the second kind, and then you work with a basis which is just you hope it's something which is a basis which is operations of Frobenius and that has computational advantage because you can see that there's less work to be done in computing the cup product matrix as well. And in fact, you can even do better. You can just start with one differential form and then apply something like the pullback by Frobenius and then subtract p times this form, and then you automatically get something which is of the second kind because you've removed all the residues. So there's some more games to be played here. Yeah, so that's
one thing you didn't put on this slide, which I thought you would, is it's enough to find just a set of generators, right? Because if you have a set of generators of wrong cohomology, computing the cup product
We'll tell you
the relations.
Yeah, you're absolutely right. Yeah. That's-
So you don't even need to sort of do that separately. You can just sort of build it into the computation at the expense of having a slightly larger matrix.
Yeah, you're absolutely right. Yeah, that's a good point. Yeah.
And how about local expansions of X, Y, or are these hard to, I think there wasn't addressed in the paper, they were taken as inputs, right? How do you find the local parameter of expansions?
Well, I think it's sort of mostly a question of actually finding a model for the curve. If you know the model, you pick a point on the missing residue disk, and then you just
Because if you don't have a local parameter yet, then computing things like Besser series is very expensive in the process, so that's really one of the markup.
Wasn't it just a Riemann-Roch computation to identify a parameter?
Those are not very good either, right? Computing elsewhere.
yeah.
Well, I'm not sure.
I actually haven't considered that. I probably have no problem with that.
Yeah, and I mean, apart from plane curves or for special plane curves, it could be automated, it could be automated. So computing the local expansions to start with.
Yeah, but to be honest, that's only a point I haven't considered seriously. Okay, so I'll pass this now to Francois.
Okay, so I'm now going to talk more on the computational part, how to concretely put that into a computer. So Amnon already detailed the algorithm. So in the input data, we have a model for a smooth complete curve over ZP or evaluation ring of some unramified extension. Maybe a extension with small ramification, I think. Yeah, this curve has to satisfy a few assumptions, but they are not too restrictive. And we need also to start with some auxiliary data. So as you mentioned, the local expansions. We also need one forms that represent the basis of each one of the complete curve, and these p and deltas that were introduced. So, well, the algorithm has already been explained. So basically, at every residue disk of every missing point, you have to find a local lift, and you have to compute the residue to get the contribution of this missing point to the matrix M2. And from that, you can recover to the matrix of the action of a semi-linear Frobenius. And from there, you can get the delta function of the spatial fiber. So one of the drawbacks is that you need a starting precision that is high enough, both in terms of P and T. If you don't have enough precision in the auxiliary data, it won't give the correct result. The complexity of this has already been mentioned by Amnon. So I think the genus, it was in terms of bits about 5 plus something, whether something depends on the curve.
Heuristically, I think we decided for painters, which
Yes, exactly.
more of a heuristics. So this is, if you can see that the complexity somehow depends on the size of the P1, P2, and delta, and so it's kind of hard, I think, to say precisely what this is going to be. Somehow heuristically, I think you expect this, or you want to reduce somehow, kind of small.
So I'll explain quickly that these residue computations, the main computations can be done with a finite precision, because the problem is that at a given missing point, once we have these expansions, we need to compute this residue, and basically we don't want to deal with infinite precision in P or with infinite Lorentz series in terms of T. So can we do that with a finite precision? So, well, let me just introduce a few notations. So in the paper we use this R alpha beta. So basically these are power series with coefficients on the left have a variation that grows fast enough. So I should have specified on the axis, the vertical axis corresponds to the valuation, and the horizontal one to M. So basically we only allow power series that lie in this gray area, in the upper plane. So the point is that once we solve for the local lift, so this more or less corresponds to another convergence condition for the local expansions. The point is that if we fix a missing point, then we can find some alpha, some overconvergence rate, such that the local lift, the forms, and the phi of omega j will all lie in this R alpha something of t, dt. So now this is interesting for residue computation. So so we just introduce this S alpha beta of n, so it's exactly the same thing but with a bounded valuation. So basically it's this picture but you truncate on the upper part, on the vertical axis. The point is that you have a well-defined multiplication between these sets. So basically when you want to compute the residue, you have this product of terms. You want to compute it up to a certain p-adic precision. We want n and n2 up to a certain precision. So since you have this overconvergence condition, one of the form will bound you on the left, the other one on the right. And since you have this multiplication, the point is that you can do all your residue computations using these objects, this S alpha beta of n. So you only need to deal with objects that have, with power series that have finitely many terms. So then you can put it into a computer from now on. So we made the basic implementation using Sage. So actually, to represent this S alpha beta of n with NTL, we had to redefine all the operations we wanted to have manually, like multiplication, matrix inversions, etc. Also, another problem was that in order to estimate this Ni, Li, etc., we need to know alpha, the overconvergence rate beforehand. So it's like a chicken and egg problem. You have to pre-compute your local equations, given your user data, your input data. Then you can estimate alpha, you can estimate the precision in t you will need, and then you have to recompute everything with a smaller precision, or you cannot compute it if you don't have enough precision. So basically, here are a few timings. So, well, it's only for elliptic and hyperelliptic examples. I wanted to produce more examples, but I didn't have enough time. So you can notice that the dependency on the genus is quite strong. And while these timings are quite slow, but I'd like to point out two things. So first of all, it has been done just for hyperelliptic curve, just by leaving out one residue disk for the point at infinity. So actually, with localizing, it seems to give better timing, like again, in average 30% on the time. I said seems to because there's a bug in the residue computation at the end, but I can estimate that the timings will be noticeably improved. And also another thing is that this current implementation has been done to deal with whatever presentation you feed it with. So it doesn't use any specific optimization. For example, if you consider an hyperelliptic curve and you solve for local lift, then you can leave out some of the equations and solve in a faster way. So these timings doesn't include any specific trick or any specific optimization. And finally, a few things that could be improved on the current implementation. So I mentioned localizing. One of the things is that so far, what happens at every missing point is completely independent. So everything could be parallelized. It hasn't been done yet. But when I say the running time would improve, it may even improve more. by just, yeah, so.
In the table, this is for the number of points, right? The number of decimal points, not for the zeta function. Or
Sorry, yes, the output was the zeta function.
what's the zeta function?
Yes,
The number
or the
points.
numerator of the, yeah.
Because for genus 9 it seems to imply. This is genus 9, right? The
Yes,
first column.
yeah, genus 9, yeah.
That's a bit strange.
And I can show you, I'll show you support to that. So yeah, as I said, it can be proved by parallelizing, computing separately what happens at every residual disk. Also, so it's the question you asked, some of the auxiliary data, the computation, you can automate part of it. For example, for equality or this kind of curves, you can pre-compute you can automate the computation of your local expansions. Things like the pin and delta, you can also pre-compute, you can also automate. Because so far, these running times, everything, all the input data have been computed beforehand. And yeah. Another thing, the problem what I told, the local equations are computed twice in the current implementation. So I think this could be modified to save some time. I also say that this implementation doesn't bother about any specific model like hyperelliptic curve or anything else. One could imagine optimized versions. And finally, the strange, or at least what surprises me, is that the bottleneck happened after you set the local expansions, the local equations, when you compute your local it and you apply it to the one form. I don't see why it would be the slowest step, but it seems to be the case. And I think Solar had to say.
Any questions for Amnon or Francois?
Yeah. Don't this P1 and P2 can degree be exponential in the genus?
What was the question?
The P1 and P2, so in the worst case, can't it be exponential in the genus, the degree? Or something like
You mean like an explicit notch down that sort of down?
I think the worst bounds are exponential, but generically.
Yeah, I mean, to be honest, I think I just put in some heuristics. I don't even remember who did these heuristics. It's so it's not a point we considered very carefully or carefully at all. Certainly something that needs to be done.
So you think for the smooth case then you get better bounds, but in general they could be bad? Is that the issue?
Yes, but I think in almost complete generality, the bounds will be much better than the worst cases. Like that.
Any other questions? If not, let's thank the speakers again.
Should we do a status report kind of see what we've done? Or you want to have a break? I need to try it. Could you speak louder, please? Huh? Louder? Status report / see where we are.
Sure.
Let me.
That would be quick, right?
Huh?
I mean, that's just a quick thing to do, right? We just sort of
Yes.
go around the room and
Shouldn't take too long.
sort of spend 10 seconds saying what we've been doing.
The way you said it sounded like very quick because you haven't done anything.
No, I mean, if you have done something, we don't want to hear a full talk about it.
Maybe I can start. I looked at the